In the last class, we learned how to calculate oxidation numbers and what the terms that are used in redox are. In this class, we want to use that stuff in order to make batteries. And that is the topic of electrochemistry, using redox reactions to make electrochemical cells. That's what they're called. I'm going to use this reaction, which if you look at it is a single displacement reaction. Zinc kicks out copper, and I'm going to show you how you can make electricity from this, but I want to show you the reaction being run in the lab first. This is the reaction as it looks if you run it in the lab. The silver strip there is actually zinc. It looks just like iron. Copper ions are blue in solution, and so if you put that strip in the copper, the solution by the end of the reaction turns colorless, and you get all that brown stuff on the bottom. The thing is, what is that brown stuff? According to the reaction here, the brown stuff is actually solid copper. It's the same thing that a penny looks like. The reason why the solution becomes colorless is that copper ions are blue in solution, but zinc ions are colorless in solution. Another thing that's important in this picture is that the copper that forms is not only in the bottom of the beaker, you also see it in another place. It is also coating the outside of the zinc strip. This is a process in chemistry that's called plating out. If you have a positive ion in the solution that's able to pick up electrons and turn back into the metal has to go somewhere, and so some of it sticks to the zinc that is already there, and it makes a thin layer on the outside of the bar. That's called a plate, and so it's called plating out. You're probably familiar with, for example, gold-plated jewelry, where there's a thin layer of gold on the outside and it's a base metal inside, but it looks just like a gold ring. There's a lot of plating out in electrochem, and we are going to discuss that as we go along. The first thing is to show that this is a redox reaction, and the way you do that is by showing that the oxidation numbers change from one side to the other. The elements zinc and copper both have an oxidation number of 0, and if you uncross the compounds, copper is +2 and so is zinc. Nitrate I'm not going to bother with because that's a spectator, and we're going to cross it out anyway. You're not going to have to worry about spectators in redox reactions because the reactions in your table that you're going to use are already net ionics, and so they don't have the spectators in them. But I want to have these reactions with the spectators to show you how it actually works in the lab. Because of the fact that the zinc goes up in oxidation number and the copper goes down in oxidation number, from that you can tell all of those other properties that we talked about last class. The substance that has an up arrow lost electrons, it was oxidized, and it's the reducing agent. The one that goes down, it gained electrons, it's reduced, and it's the oxidizing agent. In order to make a battery out of this, we first want to write the net ionic equation. And all I did was cross out the nitrate because that is a spectator. The next thing we're going to do is divide this reaction into two half reactions. If you took 131, you know you can write a redox reaction in the form of two half reactions. Each of the reactions shows half the process. One shows losing of electrons and one shows gaining. The way you do that is to keep similar substances in the same reaction and on the same side as the arrow, which I'm showing in the next slide. You put the zinc and copper as I showed, and I also included electrons. First of all, you can see why I put the electrons where I did mathematically. If you have zinc 2+, you have to add the two negative electrons to the right, because you want to end up with a neutral zinc metal on the left. But the copper 2+ is on the left, so you're going to have to stick the electrons on the left in order to make them add up to the 0 charge copper on the right. And you also know, if you balanced redox in 131, that if you add two half reactions, you can cross out if there's anything the same that's on both sides, and you especially want to make sure you cancel the electrons. And when you add, everything on the left goes on the left, everything on the right goes on the right, and then you can get back the reaction we started with. If you pick two half reactions and you don't get back the reaction you started with, you pick the wrong half reactions. Now, the zinc is losing electrons and the copper is gaining, which would make the zinc oxidation. The thing is I want to de-emphasize those two words, because chemists don't use the concept of oxidation as much as they do the gainer and loser. So that's what I want to focus on. Somehow in this topic, you absolutely have to convince yourself that you understand fully the reason why I'm saying this. If you see the electrons written on the right of a half reaction, it means that they are being lost from the stuff on the left of that reaction. So the reaction on the top here indicates that zinc solid, the metal, is losing electrons. The plus in the reaction is not a mathematical plus, it's actually just a separator. So that means that the electrons were attached to the zinc solid on the left. On the right, they're now separated from it, which means they were lost. For the copper, the electrons are on the left, which means they are being gained. You can think of it like the copper ion is slapping onto the two electrons, and they become neutral copper solid. So whenever the electrons are on the left, they are being gained. I'm showing this another way to describe it so that you can hopefully visualize why I'm saying what I do. You can think of zinc solid as being a zinc core, which in 131 they call a pseudo-noble gas core. It's not that important. What's important is that there are two electrons on the outside of the zinc. So the zinc starts out neutral because of the +2 -2. After the electrons are lost, you now have just the zinc ions that are all by themselves, because the electrons have been separated from them and they're lost. If you look at this from the perspective of copper, the copper on the left does not have the two valence electrons attached because it's the ion. When you stick the two electrons on, it becomes the metal which has the two electrons, and that is now solid copper. The thing about this is that you have to be able to see that there are actually 4 separate individual compounds or substances here. You cannot just say zinc, you cannot just say copper. You have to specify what they look like. When the electrons are either present or absent, it is a completely different substance. The zinc solid that starts out with the electrons attached, that is the silver metal that you saw in that picture. When the electrons are lost, the zinc ions go into solution, and they're now in the form of a colorless solution. The copper ions that were there at the beginning are the blue solution, and those are what the ions look like when the electrons are not attached. After the electrons get stuck on, the copper becomes the brownish metal that everybody's familiar with. So you really have to identify the fact that that if the electrons are attached or not completely changes what the substance is, and you have to specify each time which one you're talking about, either the metal or the ions. Now, since the zinc lost 2 electrons and the copper gained 2, obviously what's happening in this reaction is that the 2 electrons are being transferred from the zinc to the copper. So when they're lost, they don't just go anywhere. It's the copper that's gaining them. And so if you do this correctly, you can actually get electricity out of those electrons being transferred. In this picture, the 2 electrons are actually being transferred, but you don't see that, and you can't use it to make electricity because all that's happening is the electrons are being transferred directly from zinc to copper. What you do to make this a system that can give you electricity is you put each one of the 2 half reactions into a separate beaker. Now, what am I talking about? You put half reactions in a beaker. See, what you do is you put everything from the zinc half reaction in one beaker. So you're going to put the zinc nitrate solution, and the nitrate is a spectator, but it's still there. And you're going to dip into the solution a piece of zinc metal. So there's an interface between the solution and the metal. On the other side, you're going to take the piece of brown copper metal and dip it into a blue solution of copper nitrate, and you're starting out that way so that the half reactions are in the beakers. Now this is even worse though, because obviously there's not going to be any electricity here because they're not even touching. Electrons cannot float through the air from one to the other. What you do to get electricity is you connect the 2 pieces of metal with a wire. And you know that when you have a metal like it is in a wire, the valence electrons do not stay attached to any one particular ion. They form what's called a cloud of electrons that can move throughout the wire. That's the reason why metals conduct electricity. So if you put a negative on one side, it pushes the electrons along the wire, and that is what electricity is. Electrons moving through a wire. Each one of the sides of this is called an electrode. You can either call the piece of metal the electrode or the whole left or right side. It doesn't really matter. It's just which side is which. If you are starting this, it's not going to last very long, because as the zinc starts to lose the electrons, it's going to start developing a negative charge. As the copper starts gaining them, it's going to start developing a negative charge. The negative is going to repel the electrons and the positive is going to pull them back. So this is going to stop before it starts, really. The problem is that this is not a complete circuit unless you connect the 2 beakers. And what chemists do with a lab battery is they will connect the 2 beakers with what's called a salt bridge. There's lots of different ways of making these. I want to talk about one kind. That's a tube that goes between the 2 beakers. What's in the tube are ions. It's an electrolyte. So the solution can conduct electricity. But what they also put in there is basically Jello. Now they don't use regular Jello because Jello is a protein and it has charges on it. What they use is biology Jello, and that is agar. Same thing you make Petri dishes out of, and the carbohydrate is neutral, so it's not charged, and it's also what's called a colloid. The particles are too big to settle out, but they're not a true solution either, and there's little rivers of liquid running around the particles with the ions in them. So the agar keeps the two solutions from mixing, but the electrons allow, or I'm sorry, the ions allow conducting of electricity. So what happens now is you completed the circuit. The side that would be getting a negative charge, the negative ions from both sides of the battery migrate toward the positive. And the positives on both sides of the battery can migrate towards the negative. So this battery can continue for a while because it's now a complete circuit. The reason why they call the left side the anode is because the negative ions or anions are moving toward it. They call the other side the cathode because cations or positive ions are moving toward it. And on the left, since the electrons were on the right side of the half reaction, that means that the zinc is losing them, and the loss of electrons is oxidation. So the anode is always where oxidation happens, and it's easier to remember that because anode and oxidation both start with a vowel, and cathode and reduction both start with a consonant. Now, what's happening to the physical substances at each side of the battery? Well, I wrote the half reactions below, and the zinc solid on the left is actually losing electrons and turning into ions. If you go from a solid to ions in solution, what is that? That is actually dissolving. So the zinc electrode is actually dissolving and getting smaller. What's happening at the copper side? Well, the copper ions in the solution are picking up the electrons that are coming in, and when they pick up electrons, they turn into the metal. The metal has to go somewhere, and so it sticks to the outside of the bar. That is what's called plating out, or making a plate. So the copper electrode gets bigger. This is too slow a process to get copper falling into the bottom of the beaker like we did in that picture where he was running the reaction. So the copper sticks this time, but it makes that plate on the outside of the copper electrode. This is another kind of a salt bridge that they use in the lab. And the thing is that it's called a YouTube salt bridge. It has absolutely nothing to do with videos online. But anyway, what they do is have an electrolyte solution in the tube and glass wool in the bottom. Glass wool is something that you can use to hold the sodium and nitrate in the U-tube. Cotton is kind of dense, and so they actually use glass. And you can pick this up and take it out of one battery and put it in another one if you want to, so you can use it for more than one cell. But this is a picture of what's happening in the battery, and the thing I want to show you here is if you were going to label the electrodes positive and negative, the physicists would put a negative on the zinc and a positive on the copper. The thing is, what I told you about the zinc electrode is that it was tending to get a positive charge. So that's a problem. Is that a contradiction? It isn't. And I tried to figure out what this means. I think I now know. When you're doing a chemistry experiment, you are interested in what's happening to the battery as the battery works. As it's working, it's trying to develop a positive charge on the left. It never does because it keeps getting balanced by negative charges, but it's trying as the battery is working. The physics label, physicists are not interested in what happens when the battery starts working. They're interested in what happens before the battery is even connected. Before you connect the battery, physicists put the negative on the electrode that the electrons are going to come out of. because they say that that electrode is negative relative to the other side. See, the negative and positive physics label are not charges. They tell you which one is negative relative to the other one. So they're not a contradiction. They both say the same thing. We're not going to really use the physics label much because this is obviously chemistry. But if you looked at your car battery, or you look at a AA battery or any other one, there's going to be a plus at one electrode on one end and a negative at the other. What the negative means is that's the one that the electrons come out of. Now, if you have a battery that you're using in one device at home, do you think, let's say you had a little silver button battery that's a watch battery or a hearing aid battery, do you think that inside that battery there is two little beakers with a tube full of Jello in between them and you connect the wire? I mean, obviously, that's not what's in there. What happens is we're only looking today at batteries that you use in the lab experimentally to find out how batteries work. When you figure out the theory and how batteries work, you then turn the whole project over to a very suspicious character called a chemical engineer. These are the people who try to take the lab battery and put it into a package that you can actually insert into the device you're using. And we're going to talk about another lecture way at the end of the course where we apply thermodynamics to electrochemistry. The thing is, I'm going to show you real batteries then, and how the engineers kind of make things happen so that you can put these into the correct size package. But today, we're only going to do lab batteries because I only want to introduce you to the topic. We'll get the real batteries in the next time we talk about it. Here's another battery that I want to make out of a different reaction. And the reason I want to do this one is that it has an electrode in it that everybody uses as the standard that all the other electrodes are compared to. So let's look at this. If you look at the reaction, this is also a single displacement. The difference is that the zinc is being put into a solution of an acid instead of another metal salt. So what gets kicked out this time is hydrogen gas. This is a standard way of producing hydrogen gas, to put an active metal into an acid. But what happens is that H2 gas then is the product. You can do the same kind of analysis we did with the other reaction. The only difference is that there has to be two H pluses. So there's a 2 in front of the nitric acid because you're making H2 gas. But the hydrogen is still the one that goes down. And so that's the one that's gaining electrons. Now, if you split this up into half reactions, I did that at the bottom of the page and crossed out the nitrate again. And if you put it in the form of half reactions, the one that's losing again is the zinc, and this time the one that's gaining is the H+. The thing about this one is that in any battery, if you have an electrode, you have to have something to wrap the wire around or touch it to. The problem with the H+ reaction is that there isn't anything. How are you going to wrap a wire around H+ ions? And how are you going to wrap a wire around H2 gas? So we have to have a piece of metal at each electrode, and I want to show you how that's resolved. I showed a picture of the hydrogen containing electrode on the right. What they do is put nitric acid in solution, which is the H+ and NO3, and then there's an upside down test tube with a port that connects to a hydrogen source. And what happens is, as the pressure comes in, the hydrogen bubbles out of the solution, just like when a little kid blows bubbles in the milk through a straw. And then the piece of metal that you attach to, I'm showing as platinum. Platinum is one of the metals that's called an inert metal. It doesn't react much at all. And it's called an inert electrode because all it does is conduct electrons, but it does not react. It's the most common inert electrode. There's others that people use, but whenever I use one, I will always use platinum. And when you see the platinum, you know that it is inert. It's not going to be involved in the reaction. So that's how they provide something to connect the electrons to. Most of this cell looks pretty similar to the last one. You can call the zinc electrode the anode, and oxidation happens there, and the opposite for the hydrogen electrode. And you're still going to get dissolving of the zinc on the left, but in this particular cell you won't get any plating out because you cannot plate out hydrogen gas, which is the product. The only time you get plating out is if there's a metal ion in solution that can pick up electrons and turn into the metal and stick to the bar. The electrode with the hydrogen in it is called the standard hydrogen electrode, or the She electrode. This is the one that everyone uses to compare all the others to. Here's another picture of it, and it looks very similar, except that you can see on the right-hand side the upside-down test tube with the platinum electrode at the bottom. What I mean by everybody comparing to this electrode is that the IUPAC has determined that this electrode is the one that they're going to call 0 volts. Voltage is a property in physics that is what's called a relative property. There is no place in the universe or on Earth that's actually 0 volts. And so you're only able to measure voltage relative to another point. So this is the one they're going to define as 0 volts. And then if everybody connects to this one and subtracts, everybody gets the same answer all over the world for the voltage of a cell. And this is true that it's 0 volts in both directions because -0 is also 0. Chemists do not want to have to draw pictures of these batteries because it's cumbersome. So they have developed a shorthand notation. Notation is just how you write something for the cells. And I want to show you how these work. The way they draw this battery is that you have to put the metals at the far left and the far right, and you use a double line for the salt bridge in the middle. The salt bridge is always there, and it's always the middle of the cell. You use a single vertical line for what's called a phase separation. Now, there's 3 phases in chemistry: solid, liquid, and gas. And whenever one of them is immersed in another, there's always a boundary between them. So there's a boundary between the zinc and the zinc ions, solid and liquid, and the same with the copper. And so you use a phase separation to show that. You usually don't show the spectator ions unless they're important for some reason. And the one rule that they use in these shorthands is that you, the human being, have to take the electrode that loses electrons and put it on the left. You have to have the electrons moving from left to right. That's the standard. That means that in this battery, you can see that the zinc electrode loses and the copper gains. And that also makes the left side always the anode. because it's the one that's losing or undergoing oxidation. The thing is, when you're drawing a picture of the battery, you can draw it in either direction. See, the electrons don't know which way you drew the picture. All they do is go from zinc to copper. So if you draw the battery in reverse, the electrons are going to go in reverse. But in the in the notation, you still take the zinc and put it on the left because the zinc is the one that's losing. If you want to draw the hydrogen electrode, it's a little more challenging because there's more stuff in it. The zinc isn't going to be any different than it was the last time, but in the hydrogen side, the platinum is separated from H plus by a boundary, and the H plus is separated from H2 by a boundary. So there's actually going to be two vertical lines. It doesn't really matter which of those two you write first, H plus or H2. And I want to also tell you something that will hopefully make you more comfortable with this. I am never going to give you a picture and ask you to draw the shorthand. That takes some chemical knowledge, and sometimes you have to even look things up. And I will never give you a shorthand and ask you to draw a picture from it, because that also requires some artistic sometimes ability. The thing is, I will give you a picture and ask you questions about it, and I will give you a shorthand and ask you questions about it, but I won't make it so that you have to go from one to the other. But I have to show you one other convention that they use in the shorthand. Let's suppose that you had two ions like iron 3 and iron 2 together in the same solution. There's not really a phase boundary between them because they're in the same solution. The way chemists write that is that they use a semicolon between the two ions, because you could write those ions in either one first, because all they're doing is floating around in solution. The platinum has to go on the far left because it's the metal. Maybe they use a semicolon because they say that the ions can get through the little gap in the middle of the semicolon. I don't know. But anyway, this is what they use for two ions that are in solution together. This is a table that you're going to get to love, because this makes it so much easier to balance redox. And I want to explain what all the things in this table mean. But this is table 3 on page 11. First of all, you can see that all of the reactions in this table are half reactions. And you can also see that I set off the hydrogen reaction in the middle of the page so that it's got spaces on top and bottom, and that's 0 volts. You can also look at the fact that all of these half reactions are reductions because the electrons are being gained in each one. And that's the reason why they're called reduction. The word potentials is another word for voltage in physics. It's also called electrical potential. And it says that it's in the order of E circle red. Well, the red is obviously reduction. The circle means it's under standard conditions. We're going to talk about that in thermodynamics, but the E is the voltage. The official term for voltage in physics is electromotive force. And so I use a capital E to show voltage. And down below, it also says acidic solution. You know that you can run redox reactions in either acidic or basic conditions. This is the acidic table. And so if you look at these, what it is in English is that these are reduction half reactions and their voltages. We're going to use these in doing problems. We're not going to use the voltages much today, but in the next class we're going to use the voltages to calculate voltages of complete electrochemical cells. The voltages are arranged from negative at the top, and they keep getting more positive until the bottom. This page, page 12, is the bottom of the acidic table, which I could not fit all on one page, so the voltages keep getting more positive. This table are basic half reactions, and the voltages go the same direction, but the hydrogen electrode, where it would go is in the middle where the space is, 0 volts, but I couldn't put it in because it's an acidic reaction, not a basic one. The ones at the bottom of this page are called either acidic or basic, and those are the reduction of the halogens, which can be done the same way, either in an acid or a base. Before we get into balancing, I want to show you what the order of these voltages means. There's a reason they put them this way. I picked 3 of the equations from the acidic redox table and put them in order from negative to positive. The first thing to notice is that all of the substances on the left of the arrows are gaining electrons. And if you remember, electron gainers are oxidizing agents. So all of the substances on the left of these arrows are oxidizing agents. Now that's the zinc half reaction. If the stuff on the left is an oxidizing agent, what do you think the zinc solid on the right is? See, you know that you can turn redox reactions around if you've ever balanced by the half reaction method. If you turn the reaction around, it now shows the zinc solid losing electrons. And you know that electron losers are reducing agents. So that means that everything in the table has oxidizing agents on the left and reducing agents on the right. So I included that. And the next question we want to ask is, how good are the oxidizing and reducing agents? The only thing I want you to know today about the voltage is that a negative voltage means that it is a poor reaction, and a positive means good. What a poor reaction means is that, for example, in the first one, zinc 2+ does not want to gain electrons. Since the voltage is negative, the preferred direction of the reaction is backwards. In other words, it's more favorable for zinc solid to lose electrons in the reverse direction. That means that the oxidizing agents at the top are very poor gainers because they have negative voltages, and the oxidizing strength gets better as you go down. The exact opposite is true for reducing agents. The zinc solid at the top is a very good reducing agent because it prefers to be one. As you go down, they get poorer as the voltages get more positive. There's another table that we've used already in class that looks a lot like this, which is the acid-base table. If you remember the Ka table, all the substances on the left are acids, all the ones on the right are bases, and as the acid gets weaker, the conjugate base gets stronger, and vice versa. This is the corresponding table for redox. Now let's suppose that you want to make a really good redox reaction. Would you agree that the best way to do that would be to put a substance that loves to gain electrons with a substance that loves to lose them? In other words, you want to put a good electron gainer or oxidizing agent together with a good loser or reducing agent, and then you'll get a very good reaction. We just got done saying that the good oxidizing agents or gainers are at the lower left in the table. The good reducing agents are at the upper right. So if you mix something from the lower left with something from the upper right, you'll get a spontaneous or good reaction. And you know that the direction that the electrons will flow is always going to be from the reducing agent or the loser to the oxidizing agent or the gainer. If you look at that on this table, there's a spontaneous direction of electron flow as the table is constructed. You're always going to lose electrons from the upper right or a good reducing agent. They're going to go down the table to the lower left, which is a better oxidizing agent. It doesn't matter whether the two reactions are right next to each other in the table or very far apart. They're going to go in the same direction, upper right to lower left. The reason why I want to do this is that this is very much related to a lot of things in organic and biochem, but there's one thing in particular in biochemistry that I'm going to use as an example of this. This is the way that the electron transport chain works in biological membranes. The electron transport chain is nothing but a series of oxidizing and reducing agents, and the electrons are passed from the upper reducing agent down to another oxidizing agent. And you know that the electron transport chain from biology is the way you synthesize almost all the ATP in your body, and it's also the way that plants use to run the dark reactions that synthesize food for animals. So I'm going to show you a picture of the electron transport chain later, but let's finish this inorganic part and then I'll apply it. Let's show the spontaneous direction with the zinc and hydrogen cell. If you connect zinc and hydrogen, you would expect the electrons to go from zinc solid down to hydrogen. And there it is, they do, from zinc to hydrogen. If you put together zinc and copper, you would expect the electrons to go from zinc down to copper. And here's that cell. I put this in the form of rules, although you don't really need them specifically, that if you take two half reactions in the table and make a battery out of them, the electrons will always go from the upper reaction down to the lower one. That means the upper half reaction is the one that will lose the electrons. And more specifically, since you have to go from a reducing agent to an oxidizing agent, the direction is going to be upper right to lower left. This is an example where I copied 3 of the reactions out of the acidic table. They're in order of voltage, and so the question asks which substance is the best reducing agent. Now, you are not allowed to answer just magnesium, nickel, or tin, SN, because there are actually 6 substances up here. You remember that the ions of the metal have completely different properties. You have to specify which one you're talking about. The best reducing agents, we said, are at the upper right in the table, and therefore magnesium solid is going to be the best reducing agent. We said that the best oxidizing agents are at the lower left. which means that the SN2 plus is going to be the best oxidizing agent. Now you can use these for another purpose. Let's suppose that you wanted to take two of the reactions and make a battery out of them. I took one of the reactions out. If you wanted to make a battery out of the first two reactions, and you made one beaker that had the magnesium half reaction in it, and another beaker that had the nickel half reaction in it, and you connected them with a wire, which way would the electrons go? You can tell that since you go from upper to lower, you're going to go, the electrons are going to travel from the magnesium to the nickel, and that will tell you the direction they go in the wire. This is what the cell would look like, and because magnesium is above nickel in the table, the electrons will go from magnesium to nickel. This is a picture of the electron transport chain in a mitochondrion. Mitochondria, of course, are the ones that synthesize ATP and store it. So in a mitochondrion, the ATP has to be synthesized on the inside of the organelle because you want to store it in there. The way this works is that there is an electron transport chain in the membrane of the mitochondrion, in the internal membrane. Mitochondria have two membranes. The complexes are numbered. We're only going to talk about 1, 3, and 4 because the one that's the complex 2 is kind of an unusual one, which only is at one step, so I don't really want to talk about that one. But what happens inside the mitochondrion is the Krebs cycle, or the citric acid cycle. The main product from the citric acid cycle is not ATP. The main product of the citric acid cycle is a molecule called NADH. And that it has on it what's called a high energy hydride. The H transfers 2 electrons to an upper acceptor, complex 1, in the electron transport chain. And these have a series of falls of the electrons from upper right to lower left. So when the electrons fall from complex 1 down to complex 3, it provides energy to pump out H pluses into the area between the membranes, and when the H plus flows back over the enzyme ATP synthase, that's how you take the phosphate and stick it onto ADP to make ATP. Then the electrons fall a second time from complex 3 to complex 4, and another H plus gets pumped out, so you can get a second ATP. And then what is the terminal acceptor that causes the third fall that synthesizes a third ATP? That is the reason why we breathe oxygen. O2 is the terminal acceptor of the electrons that are coming down the electron transport chain. If we didn't breathe anything that accepted electrons, the electrons would back up in the chain and you wouldn't be able to get any ATP, even if you were metabolizing. The O2 turns into water when it gets reduced. So that's where the water comes from that you breathe out. The CO2 comes from the Krebs cycle. So when you breathe out CO2 and water vapor, CO2 comes from the cycle and water comes from oxygen accepting electrons. Another organelle that has an electron transport chain is a chloroplast. You know that chloroplasts are what gather light and turn it into ATP for you using the light from the sun. The thing about a chloroplast membrane is that it's just like a mitochondrial membrane, sort of, except it's inside out, because you need the ATP on the outside of the organelle, not the inside. And I'm going to talk about why that is, but if you look at this system, there are also 3 complexes in the membrane. The thing is, it is not the energy from metabolism that promotes the electron to the upper acceptor, it's light. And so light energy falls on the first acceptor, the electrons are promoted, and where do the electrons come from? They come from water. So when you take the electrons away from water, the water gets converted back to O2. You know this system, right? That animals breathe O2, but when plants synthesize, they produce O2, and so it's a cycle. The plants produce it, animals use it, and it makes a cycle. Now, once the electrons get to the upper acceptor, they fall 3 times again, and you can get 3 ATPs out, just like in a mitochondrion, but there's a second step where light can fall on another acceptor, and instead of being used for ATP, it's used to synthesize a molecule called NADPH. Animals don't have much of this, and the reason why the NADPH and the ATP have to be synthesized on the outside is that is what plants use to take CO2 and water and put them back together in the dark reactions to synthesize sugars. That's where the dark reactions happen, in the cytoplasm. And if you take a mitochondrial membrane, you can turn it inside out with detergent. And the same with a chloroplast membrane. If you take a mitochondrial membrane and turn it inside out, it will still synthesize ATP, but it'll synthesize it on the outside instead of the inside. This is a really interesting system. And so animals are able to burn energy and produce ATP because they have an electron transport chain. And plants are able to absorb light and make food for animals because they have an electron transport chain. So redox is really a big deal in biology. Now, during this part of the class, I want to show you how to balance redox reactions using those half reactions from the tables. Now, I'm going to do 5 example problems, and if you can follow these and do step by step and actually find the things that I'm talking about in the redox tables, you will never have to worry about balancing redox again, because you can do it strictly by recognition and least common multiple. So let me show you this. Now, in order to balance a reaction, though, you know that those 4 things I have listed have to be true. There has to be the same number of atoms of each type on each side. But in a redox reaction, charges also have to balance. That you don't really have to worry about, though, because since there's electrons involved, if you get the electrons equal to each other in each of the half reactions before you add, the charges will automatically balance. Now, the last thing is that you can only have a substance on one side of the arrow. You can't have the same substance on both. I'm going to show that by using examples rather than trying to explain it now. Now, I'm pretty sure you know that if half reactions are run under acidic conditions, the half reactions can contain H+ and water because it's an acid. They don't always contain those because sometimes they're not needed to balance, but they are allowed to. But you are not allowed to have OH in an acidic reaction because OH is the base ion. It's the reverse for basic reactions. They can have OH and water, but H plus cannot be allowed. This is the table for acidic, and these half reactions often don't have either H plus or water. A lot of the reason for that is that the ions don't even exist in a base. For example, if you put aluminum ions into a base, they form AlOH3 solid, and you won't even be able to have the ions. That's the reason why a lot of these are in the acidic table. But if you look at the ones at the bottom of the acidic table, you'll be able to find many of them, not all of them, but many of them have both H plus and H2O present. Basically, you use those anytime you need to balance. You're going to be using half reactions from this table to balance. In the basic table, a lot of the reactions have either OH minus or water or both, but you will never find H plus in a basic reaction. The ones at the bottom of the table can be used in either acidic or basic. This is the first example, and this is how I ask a balancing of redox. I show you the two things that react and the two things that form, and I have to tell you somehow whether the reaction is acidic or basic. Sometimes you can tell by whether there's H plus or OH in the reaction, but I usually just tell you. In order to balance an equation like this, you can see that this one is not balanced as it is. There's oxygen on the left, but not on the right, so the atoms don't balance, and the charges don't balance. There's a -1 charge on the left and +4 on the right. The first step always in balancing these is to find two half reactions in the table, and you find similar substances. One of the half reactions is going to have to contain MnO4 minus and Mn2 plus. The other one is going to have to contain nickel solid and Ni2 plus. So let's go to the acidic table and find them. The reaction that contains MnO4 minus and Mn2 plus is the one I pointed to here. All you do is copy it as is. In 131, you would have had to add the 8 H pluses and the 4 waters and the 5 electrons. You don't have to do any of that. I saved you all those steps. All you have to do is copy this exactly as it is. And so that's what I did here first. The other half reaction has to contain the other two substances, nickel 2 plus and nickel solid, and I'm pointing to it here. Doesn't matter which side the two things are on yet, as long as it's the two exact things that are in the equation. So I copied them exactly as they are, and now the next step is that you will always have to turn one of these around. You can't add redox reactions if the electrons are on the same side, because the electrons have to cancel. The number lost has to equal the number gained. The way you decide which of these to turn around is that you have to keep all the substances on the same side of the arrows as I gave it. In other words, I gave MnO4 minus on the left in the problem. When you copied the half reaction from the table, MnO4 is already on the left. So you don't have to do anything with the Mn reaction. But I put nickel solid on the left. But when you copied the half reaction out of the table, Ni solid was on the right. That means you must turn around the nickel reaction in order to get everything on the same side I gave it. Once the reactions are turned around, the thing about balancing is you have to equalize the electrons. The way you do this is by multiplying each equation by a factor. This is what's called the least common multiple in math. When you're deciding on it, you only look at the electrons. Don't look at any other coefficients. Since there's 5 electrons in the top reaction and 2 in the bottom one, it's kind of like crossing. You're going to multiply the top equation by 2 and the bottom equation by 5, and then there'll be 10 electrons in each one. Now, when you multiply the equations, what do you multiply? You certainly can't change the formulas, so what you do is you multiply the coefficients. You go all the way across and multiply all the coefficients by the number in front. So you see that the MnO4 reaction ended up to be 2MnO4, 8 times 2 is 16H plus, 5 times 2 is 10 electrons, etc. We went all the way across and multiplied. The same with the bottom one, multiplied by 5. Now you have 10 electrons in each reaction. Once you've equalized the electrons, you can now add. When you have the same on both sides, you can cancel them. And all you have to do is copy everything that's left. You copy everything on the left, and you copy everything on the right, and you have a balanced equation. It doesn't matter what order the substances are written in as long as they're on the right side of the arrow. I'm only going to do this in this one problem, but I'm going to show you that this really is balanced. Let's count the atoms. Can you see that there's 2 Mn's on each side? 5 nickels, 16 H's on the left, and there's 8 times 2 or 16 on the right. And the oxygen on the left, 2 times 4, and on the right there's 8 from the water. So the the atoms balance. What about the charges? We're talking about the overall charge. For MnO4 minus, there's 2 of them, that's minus 2. Nickel is neutral. I would have put a charge if there was one. And for the H, there's 16 plus 1 H's, which is plus 16. If you add those up, it comes out to plus 14 on the left. On the other side, the manganese, 2 times 2 is 4. And for the nickel, 5 times 2 is 10. Water is neutral, so that side adds up to 14 also. That means that somewhere along the way, 14 spectators have been crossed out. 14 minus charges have been crossed out, but we don't care about them. We're only doing that ionic. The other question that I ask about these is to determine which one is the oxidizing agent and which one is the reducing agent. There are actually 2 different ways to do this. And one way to do it is by calculating the oxidation numbers on each side and seeing which ones changed. So the first thing we would have to do is calculate the oxidation number of Mn in permanganate. We did problems like this at the end of class last time. Put a -2 above the oxygen, X above the manganese, has to add up to -1, and so the Mn comes out to +7. For the Ni solid, obviously it's 0 because it's an element. On the other side, Mn2 plus is +2. There's nothing to do, and the same with Ni2 plus. So, since Mn goes from +7 to +2, that's down, and that makes it a gainer, which is an oxidizing agent. And nickel goes up, so that's the reducing agent. So whichever one has the down arrow is the oxidizing agent. Whichever one has the up arrow is the reducing agent. But there's an even better way to do this, which is, I think, easier, because remember, all you're looking for is the loser and the gainer. So you can go back to look at which equation you turned around. The manganese equation is the one that you did not turn around from how it is in the table, which means the electrons are still on the left, which means that that shows MnO4 minus is the gainer or the oxidizing agent. But you had to turn around the nickel one, and that put the electrons on the right, which means they're being lost. So that makes nickel solid the reducing agent, not the nickel 2 plus, but it's the nickel solid that's actually losing, and so that one is the one that's the reducing agent. This is another way to do it. So in addition to doing it by the oxidation number, you can call the oxidizing agent the one that still has the electrons on the left in the half reaction. The reducing agent is the one you turned around and has the electrons on the right. This one is an example of a basic redox equation, and the difference in this one is that we're going to end up with things at the end that we have to do a little bit extra. So let's take a look. You have to first find an equation that has ClO3 minus and ClO4 minus, and that you have to find in the basic table this time. So I pointed to the reaction that has those two things in it. You have to be really careful when you're doing this because you have to have exactly those two things. You cannot have, there's a lot of things in there, but you can't have ClO2 minus, you can't have ClO minus, you can't have Cl minus, because those are not exactly what I gave you. You have to make sure that the equation has exactly the two things I gave you, and the one I'm pointing to is the one. The second equation here has got to have MnO4 minus and MnO2. So we go back to the basic redox table, and if you go down and find the one that has exactly the same two, it's the one I'm pointing to. There is an equation further up right before the space that has MnO2 and MnOH2, but that's the wrong one because it's not exactly the same two things. So I copied the two half reactions, and now we have to decide which one to turn around. If you look at the chlorine reaction, ClO4 is on the left in the reaction that you copied from the table, but in my given equation, ClO4 is on the right. That means that the one you have to turn around is the chlorine equation this time, because you have to get everything on the same side as I gave it. The next step then is to always look at the electrons and get them equal. Don't look at any of the other coefficients, just look at the 3 electrons in the bottom and 2 on the top. You're going to have to cross, so you're going to multiply the top one by 3 and the bottom one by 2. And again, when you do this, you multiply the coefficients by the factors. So I multiplied the first equation all the way across by 3, and I multiplied the second equation all the way across by 2. Now you have 6 electrons in each equation, and you can add. So since the electrons are equal, you can cancel them. But if you look at the equation, you also have water still on both sides and OH still on both sides. You have to get rid of the extra. And in order to do that, you're going to subtract whatever the smallest amount is from each side. So I want to subtract 3 waters from both sides to get rid of it. If you do that, the water, 3H2O in the first equation cancels, and the 4 turns into a 1 in the second one. You also have to cancel the extra OH. So I'm going to subtract 6 OHs from both sides. That gets rid of the 6 OH, and it turns the 8 into 2. So when you're done, all you have to do is copy what's left, and the equation that I have written there is everything and it's balanced. You have to eliminate the extra, otherwise the equation is wrong and it's not considered finished. I showed here that the atoms and the charges both balance. If you look at the charges this time, we have 3 negatives on the left and plus 2 negatives, that's -5. And on the right, we have 3 negatives and 2 negatives, that's -5 also, so the charges do balance. To determine the oxidizing and reducing agent, you can calculate the oxidation numbers, but it's going to be a lot longer this time because there are more of them to calculate. You would have to calculate the oxidation number of manganese in MnO4 and get +7. You would have to do the Mn in MnO2 and get +4. The Cl in ClO3 minus comes out to +5. And the Cl in ClO4 comes out to +7. So if you evaluate the changes, chlorine goes from +5 on the left to +7 on the right, which is up. And so that makes ClO3 the reducing agent because it's the loser. manganese goes from +7 on the left to +4 on the right. That's down. That makes it the gainer or the oxidizing agent. You can also do it by looking at the equations. The reducing agent is the one that you turn around. So you had to turn around the Cl equation. The electrons end up on the right. That makes ClO3 minus the reducing agent. The oxidizing agent is MnO4 minus, which you did not turn around. The electrons are still on the right, on the left, and they're being gained. So you can always use both of these methods. The electrons on the left mean it's the oxidizing agent, and the electrons on the right, which you turned around, mean it's the reducing agent. This equation has actually got 3 substances on each side. Doesn't make any difference. You still have to find only 2 half reactions. You can't have 3 half reactions because that's 1 1/2. This is only one equation, so we have to find 1 half reaction that's got AuCl4 minus and Au solid gold. And since I said it was acidic, there's the equation in the acidic table, and I just copy it. The other equation will have to have silver solid and AgI. The equation that has both of those things is 3 up from the hydrogen here in page 11, and so I copy it. If you look at those equations, even though we only looked up 2 half reactions, the extra substances showed up. The Cl minus showed up in the first one and the I minus in the second one, and if you do it right, that will always happen. So we just have to turn around and add, and you can see that the silver equation is the one that has to be turned around because the AgI has to end up on the right, which is the same as where I gave it. So all I have to do here is multiply by 3 to make the electrons equal. I multiply the second equation by 3. When I do it, here's what it comes out, 3 electrons in each one. You can cross out the electrons and add, and you get the balanced equation. And again, you can do which one is the oxidizing and reducing agent either by calculating the oxidation numbers or by looking at which direction you turned around the reactions in. Since the one that stayed the same is the AuCl4 minus reaction, that is the one that's the oxidizing agent. And since the one you turned around is the silver, that means that AgS is the reducing agent. So the one with the electron on the left of the half reaction is the oxidizing agent, and the one with the electron on the right is the reducing agent. I also want you to be able to write balanced equations for these shorthand notations. This is not a reaction, this is a shorthand of a picture. It has aluminum in one beaker and the chromium ions in the other beaker. Platinum is always inert, so it won't be in the equation. I want to show you what a picture, so you need to find a half reaction for the aluminum on the left-hand side and another half reaction for the chromium ones on the right. This is what the picture of this cell would look like. It's a piece of aluminum in a solution of aluminum ions, and it's a piece of platinum metal in a solution that contains all 3 of the ions on the right. You can see those ions have no order to them, and so I could have written them in whatever order I wanted because they're just floating around in the solution. We need to find a half reaction for both sides, and so we'll look for the aluminum one first. The aluminum half reaction is at the top of page 11. So I just copied it directly from the table. The chromium half reaction, and that's the memory ion dichromate, Cr2O7 2-. The equation for that one is about 2/3 of the way down on page 12. So I just copy that one. Now, this is the big thing about writing the equation for one of these notations. You have to turn around the correct half reaction. If you remember, I said that you, the human being, have to put the one that loses electrons on the left. That means that in this notation, the aluminum is the one that's going to be losing the electrons. But if you look at the equation for aluminum that you copied out of the table, aluminum is actually gaining electrons. So here in the picture, you can see the electrons are on the wrong side for aluminum because the aluminum has to lose. So the aluminum reaction is the one that has to be turned around because you need to have the electrons on the right of the half reaction. The idea is that if you can remember this, you'll always be okay. You always turn around the stuff on the left of the double line, and it's usually the first equation you write. You just have to remember that that is the one you turn around, and you'll be fine. If you notice, the order in the notation has nothing to do with which way the reaction goes. You write the reaction the way it is from the table, and however it is from the table, that's what you turn around. After you turn it around, you then have to equalize the electrons. This is one where you don't want to just multiply the top one by 6 and the bottom one by 3 because that's going to give you a multiple. You also cannot have a multiple of the reaction because that's wrong also. You have to get the least common multiple. The least common multiple between 3 and 6, of course, is 6. And so all you have to do is multiply the top equation by 2. So when you multiply the top equation by 2, it comes out on the next slide. Once the reaction is turned around and the electrons are equal, you can then add. And when you add, you just copy everything that's left after you cross out the electrons, and that's the equation. You can figure out the oxidizing and reducing agent by doing the oxidation numbers just as we did before. So chromium in dichromate comes out to +6. So if you look closely at them, you can see that chromium goes from +6 to +3. That is down, so that makes it the oxidizing agent. Aluminum goes from 0 on the left to +3 on the right. That's up. That makes it the reducing agent. The aluminum solid is the reducing agent because that's the reaction you turned around. So the aluminum solid is losing. Cr2O7 is the oxidizing agent because it's the one that you did not turn around, and it's gaining electrons. And here it is summarized on the slide. And this is another one of these type. This one is just basic. You can see that it's got OH in it, which means you're going to look in the basic table. The first reaction that you have to find is the one for iron on the left. And here it is in the table. It's got both of those substances in it, and they're the same two substances. You can't use any other reaction with iron in it because you have to have those exact two things. So I just copied it directly out of the table, and of course it's possible for it to have OH in it because it's a basic reaction. The reason why the reaction for the right-hand side is a little bit more difficult to find is that in the basic table, OH can be in any of the reactions, so that's not unique, and platinum will not be in the reaction. So that means you have to find the one and only one basic reaction that actually has O2 gas in it. I'm pointing to it in the basic table, and that is the only one with O2, but of course there's oxygen in all kinds of the reactions. And for example, in HO2, that is not the same as O2 gas. So you have to get the exact one that has O2 gas in it and copy it. Now, as far as which one you turn around, you always turn around the stuff on the left, which will usually be the first equation you write. So I turn around the iron. When I do that, all I have to do to equalize the electrons is multiply the top equation by 2. So when you multiply the top equation by 2, you end up with 4 electrons in each one. In this reaction, when you add, both the OHs and the electrons cancel. That's no problem, even though OH is not in the final equation. You know that you're running it under basic conditions, so it's fine. The only one of these least common multiples that I think you might have trouble with is that there are some equations with 6 electrons on one side and 10 on the other. And the least common multiple is not 60 here, it is 30. If you multiply the top equation by 5 and the bottom one by 3, you end up with 30 electrons in each one that can cancel, and that is the one that is a little bit different. Here you can see that oxygen is the oxidizing agent. That's not unusual, is it? Oxygen, because it goes from 0 to -2, and iron is the reducing agent because it goes from 0 to +2. And you can also tell that the oxygen is the oxidizing agent because the electrons are on the left in the half reaction. That's the one that you did not turn around. And the iron solid is the reducing agent because that's the reaction you did turn around. So you can also tell from the way the equations are pointing. Now this is table 4 in your book, and you're going to really like this one because, believe it or not, I took all of the equations from the other tables, copied and pasted them, and I put them in this table in alphabetical order. Now if you look for silver under SI, you're still not going to find it, but if you look under the correct symbol, you'll be able to locate some of these long, strange-looking compounds by doing them in alphabetical order. The only problem in this table is that you have to realize that the basic and acidic are all together. And so I did not put a symbol next to the acidic ones. I put a star next to the basic ones, and I put a slash next to the ones that can be either acidic or basic. And you also have to realize that the voltages are no longer in order because we're going by alphabetical order. If you go along this table, you get to the C's and then the F's, and the next thing you see is a heading. If you look at that heading, what are those substances? Well, everybody knows H2 and O2 are the elements. Water is the liquid, and the thing is, what is H2O2? This is the compound we said was called hydrogen peroxide. There's another thing in there, HO2 minus, and we haven't looked at that yet, so I want to see what that is. The thing is, I couldn't separate those reactions really from each other because they're so interrelated, so I just left them in a group. The place where the HO2 minus comes from is related to the fact that H2O2 is also a weak acid, which is listed in table 2. It can only lose one H because the second H will not come off in water, but here it is listed as a weak acid in table 2. The thing about weak acids, hydrogen peroxide, as well as any others, is that if you put them under acidic conditions, the H plus increases and you will shift to the left. Basically what it is that under acidic conditions you stick the H on, and the predominant form is the weak acid itself, which has the H stuck. But if you put hydrogen peroxide into a base, the OH is going to react with the H plus and eat it and shift the reaction to the right. It basically pulls off the H, and so in a redox reaction that's basic, peroxide will be written as HO2 minus. In the two reactions I'm pointing to, they're both acidic, and H2O2 is written as H2O2. But in the basic reaction, the peroxide is written as HO2 minus. That's with the H plus pulled off. If you continue along the table, you run into another heading, which has HNO2, NO2 minus, and NO3 minus. The same thing happens with HNO2 that happens with peroxide because it is also a weak acid. If you put HNO2 in under acidic conditions, you'll write it as HNO2 with the H stuck. But if you put HNO2 under basic conditions, the base will pull off the H and you're going to write it as NO2 minus. What's instructive about this is that NO3 minus also comes from an acid, but it comes from a strong acid. And so it doesn't make any difference whether you're under acidic or basic conditions. NO3 can never accept an H+, and so that means it's always written as NO3 minus either way. The two reactions I'm pointing to are acidic, and so HNO2 is written as HNO2. In these two reactions, which are basic, it's written as NO2 minus. Several of the equations contain NO3 minus, but whether it's acidic or basic, the NO3 minus is written without the H attached. And here's the end of the alphabetical table. In this homework, I wanted to have you know how to label the different parts of a battery as the anode and which side is the reduction and which all of these things we asked in class. So the first problem on the homework, I didn't really know how to ask that, so all I did was make a picture of an actual cell, and I asked you to label the parts. I want you to use that question to really get an understanding of how the cells are put together and which side is which. The key to it is whichever side the electrons are coming out of, that side is the one where they're being lost, and you can get everything else from that. And I just ask you to look at that question and make sure that you know how to label all those parts of the cell. There's another question about identifying oxidation or reduction, and most of this homework, though, is balancing. I give you 5 of the double line notation problems, and I want you to write a balanced equation for them. Remember that in those equations, the left side is always the anode. And then I have 10 basic equations and 10 acidic ones. And if you can balance all of those, you have really got the balancing down pat. Please use the tables and not the 131 method. And I also tell you the oxidizing and reducing agent in each one, so you can learn better to identify those. So that is homework 5, and if you can do homework 5, you're caught up. And in the next class, we're going to start a new topic, which is buffers.